Hello students, welcome back to the chemistry class, and here with you Nagarjuna, and I'll be taking you through a very interesting and important topic of chemistry today, that is organic chemistry. In fact, it's a special branch of chemistry which deals with the organic compounds. So how does it is more important and it is more interesting? For example, let's take the things around us. The food we eat is organic. That means the food means generally in chemistry terminology, if you want to tell, those are carbohydrates, proteins, right? All these are organic, and the plants around us, animal being, and the nature around us, and the human beings, all are constructed of the organic substances, like our human body, animal body, plant body, everything is constructed of organic substances, and the food we are eating is organic, and the medicines we are taking are organic, right? And nowadays you might have heard of that everywhere, organic vegetables, organic fruits, right? So that's how it's an important area and a significant branch of chemistry, right? So let me just go through it and let me just introduce that organic chemistry to you in this today's discussion. So let's get into that. So organic chemistry some basic principles and techniques. Some basic principles and techniques. First of all, let me give you the definition. What is this branch of chemistry? And what is its significance? Just now I told you. And what is the definition? Organic chemistry is a branch of chemistry which deals with the carbon's compounds. Organic chemistry is the study of the carbon compounds, right? Now, how does a single elements chemistry, single elements compound, have a special branch of chemistry? What is the speciality with this element? So this element has some unique properties apart from the other elements. Like, for example, if you see overall 118 elements are present at present, right? So out of 118 elements all together, which were having around 6 millions of compounds, maybe 8 millions of compounds, but carbon alone is having approximately 22 millions of compounds. 22 millions of compounds, so that scientists have dedicated a special area to study its compounds. Now let's have a look into that. What are those properties making this carbon so special and which are allowing the carbon to make such many compounds? Let me just take you those properties. The first property is its tetravalency. Tetravalency, the meaning is can form 4 covalent bonds. Carbon can form 4 covalent bonds. And the second property is its catenation property. Catenation. What is catenation? Catenation is a property of an element to combine among themselves, the same type of atoms combine themselves and they form a huge network type of molecules. Just like when you observe a fishing net, the identical type shapes will be there in the fishing net that spreads like a huge network. So just like that, that is the catenation. So let me just write it for your reference here. Catenation is the property of an element to form large range network molecules, right? By combining among themselves. That means carbon is showing catenation means the atoms of the carbon itself, the same kind of atoms combine among themselves and they form a huge network, just like as I was telling as a fishing net, right? So this property, the catenation property, is highest for the carbon among all the elements. There are some other elements also which can show the property of catenation, but carbon has the highest magnitude of catenation. And the third property is its ability to form multiple covalent bonds. Multiple covalent bonds. Multiple covalent bond means more than one covalent bond between the two carbon atoms or carbon with any other atoms. So multiple covalent bonds, which means multiple covalent bonds, and it can also changes its mode of bonding based on the requirement. For example, let me just elaborate it. Carbon can form the 4 covalent bond, as the valency of carbon is 4. It can form 4 single bonds around it, or it can form 2 single bonds and 1 double bond around it, or it can form 1 single bond, 1 triple bond around it, or it can form 2 double bonds around it. See, everywhere the covalency, I mean the number of bonds around the carbon are 4 itself, but the way it is bonding is different. In the periodic table, this is the only element which has this many flexibilities of changing bonding mode. So this is an extraordinary property that carbon has, the multiple covalency, right? And the last property is it can combine with almost all the elements in the periodic table. For example, because as its capacity to combine with more and more number of the elements increases, the number of compounds that are going to be formed will get multiplied. So for example, let me just take a small example. I take an element can combine with X and Y. So what are the possible combinations of compounds that I can write? From this, AX can be formed, AY can be formed, AXY can be formed. That means 3 combinations are possible, so that it is forming 3 compounds. Now, for the sake of this, I am taking another element which can combine with 3 other elements. Element B can combine with X, can Y, and it can also combine with Z. In these combinations, binary compounds are also possible in the beginning. That means BX, BY, BZ, BXY, BXZ, BYZ, and finally BXYZ. See, as its capacity to combine just one elements increased, right? Increasing of one element is making a huge difference in the number of compounds that are going to be formed. So that's how carbon can combine with almost maximum number of elements in the periodic table. So all these properties togetherly making carbon so special and allowing it to form that many number of compounds. So that was about carbon and its special properties. And the next thing that we are going to discuss here is about the name organic, right? So in ancient days, scientists used to name the organic compounds mainly based on the source of extraction, right? So in that case, a scientist called Berzelius, the first attempt to classify the compounds into organic and inorganic. Actually, he classified the world into 2 classes, right? The living one, the living world, non-living world. Right. Now he classified the surroundings like this, living world and the non-living world, and he named the substances whichever are obtained from the living world, I mean the living sources. Living sources means animals and plants, right? So these are the substances which are obtained from the living sources. Those are organic, and the substances which are obtained from the non-living sources are he named as inorganic. Right? So the compounds obtained from the living organisms are named as organic compounds, and the substance which is obtained from a non-living source is named as inorganic. And for this he explained his proposal with a theory. He proposed vital force theory. Vital force theory he proposed to justify his proposal. So according to which living things, I mean the animals and plants, have vital force in them. Vital force in them which is responsible for the synthesis of organic chemistry. I mean the organic compounds. So according to him, vital force is the necessary force that is required to synthesize the organic compounds. That too, it is only present in the living organisms, so that it is only possible to obtain the organic compounds as it is, whichever are available from the living sources, and we cannot synthesize the organic compounds individually, I mean in the laboratory. Why? Because in the laboratory you cannot create the life, so that we don't have a vital force in that. That's the reason he said it can only be obtained from the nature, I mean the living organisms, and cannot be synthesized in the laboratory artificially. So that was his vital force theory. Then later one of his student, after some period, over a period of time, one of his student, Frederick Euler, who proved that organic compounds can also be synthesized from the non-living sources, I mean from the inorganic compounds. For that, what he did, he took a salt of ammonium cyanate. So let me just give you the name also, ammonium cyanate, and when it is heated on thermal decomposition, it has isomerized into a new compound which has surprised the entire scientific society and which has given a breakthrough for the old proposal of having not synthesized in the laboratory. That means a compound which he got is urea, right? And we all know that the mammals' urine, animals' urine, humans' urine, which contains uric acid. So this urea is the main constituent of the uric acid, which means it is synthesized in the human body and the animal body. That means it's an organic compound, and which is synthesized in the laboratory from an inorganic compound. So let me just mark that also. Inorganic, and this is organic. Hence it is proved that an organic compound is synthesized from an inorganic compound, right? So later this vital force theory was discarded. Then after his experiment, that Frederick Euler has proved that organic compounds can be synthesized from the inorganic sources, and that too in the laboratory. Then that has given a pathway, that has shown a pathway for the next scientist, that yes, we can synthesize the organic compounds artificially also. Let's try in that way. In that way, there are many scientists succeeded, among which Kolbe. This name you will be listening many times throughout the organic chemistry. A very famous scientist, has the contribution in many areas of organic chemistry. So Kolbe synthesized acetic acid. As we all know, the formula of acetic acid is CH3COOH. And one more scientist called Berthelot, who has synthesized methane. What is methane? Nowadays you might be seeing natural gas, CNG gas, right? Methane is called natural gas, and the cylinder CNG gas means the autos and the automobiles which are running by using the CNG. CNG nothing but compressed methane only, compressed natural gas. So what is this? The natural gas, which is a clean fuel and less expensive fuel as well, right? So nowadays the governments have encouraging such kind of fuels to reduce the expenses of traveling, and eco-friendly fuels, clean fuels, which do not evolve or release the toxic impurities into the atmosphere. So this is one among them, and which is also a cheaper fuel, right? So after that, scientists have come to know there should be a new definition. So in the beginning, in the beginning era, most of the compounds which they known extracted from either from the plants and the animals and from the earth's crust. Earth's crust means mainly fuels, the crude oil, petrol, diesel, and this methane, natural gas, and others, kerosene, naphthalene, everything. All the substances are made up of only two elements commonly, that is carbon and hydrogen. Then they gave a definition that hydrocarbons are the fundamental organic compounds. Hydrocarbons which are made up of carbon and hydrogen are the fundamental organic compounds. And the rest of the families are the derivatives of organic fundamental compounds. What are organic fundamental compounds? Just now we have discussed. Those are what? Hydrocarbons, right? So by observing all the fact, hydrocarbons are concluded as the fundamental organic compounds, and the rest are the derivatives of the hydrocarbons. Rest means only organic. Whatever the rest of the organic compounds, those are the derivatives of hydrocarbons. And what does that mean? This means by replacing one or more hydrogens from a hydrocarbon with the different types of functional groups, you can derive the variety of the organic families. Let me just illustrate this. For example, I take this RH. Let it be any hydrocarbon group. It may be alkane group, it may be alkene group, it may be alkane group. Hydrocarbon group. It doesn't matter whether it is saturated or not. Now just I have highlighted one carbon hydrogen bond. This is the hydrogen I would like to replace, right? Now if I replace that with a OH group, you get ROH, and this compound is called alcohol. And if I replace that with a COOH group, and that particular compound which we get is called carboxylic acid. So that's how we can get the variety of organic compounds and its families by replacing one or more hydrogens from a hydrocarbon. Yes. So after that, the types of hydrocarbons and the derivatives of hydrocarbons as we discussed. So it is concluded that hydrocarbons are the fundamental organic compounds. So let's have a classification. What type of hydrocarbons that we have in our context? I mean in our syllabus. So this is acyclic hydrocarbons. Acyclic means open chain, and cyclic hydrocarbons or closed chain hydrocarbons. Acyclic hydrocarbons or open chain hydrocarbons again have two subclasses. Those are saturated and unsaturated. right? Saturated hydrocarbons are those which have only CC single bond. Carbon is always having single bonds around it. So those are what? Alkanes. And the molecular formula of alkanes is CnH2n plus 2. An example if I would like to give is CH3, which we call it as what? Ethane. Now, unsaturated hydrocarbons. Unsaturated hydrocarbons means either carbon-carbon double bond or carbon-carbon triple bond. So here, an alkene which has a carbon-carbon double bond and whose molecular formula is CnH2n. And example, the next compound I will take unsaturated compound with 2 carbons, so we can better correlate. See, same 2 carbons, but here it is a single bond, so it's saturated. Here it is a double bond, so it's an unsaturated, right? The other one, I mean in the unsaturated family, that is alkyne, which have a CC triple bond whose molecular formula is CnH2n minus 2, and the example is CH triple bond CH. See, now you can see CC single bond, CC double bond and CC triple bond. So these two are having multiple covalent bonds among carbon and carbon, so they are unsaturated. This is having only single bond among 2 carbons, that is saturated, right? So this is how we classify the saturated and unsaturated hydrocarbons. Now the cyclic hydrocarbons are alicyclic, aromatic. What are aromatic compounds and how can we say whether it is aromatic or alicyclic? That is another discussion. When we discuss about aromatic hydrocarbons, we will be dealing with it. As of now, strictly we just go through the classification of hydrocarbons, right? So alicyclic are carbocyclic and heterocyclic. Carbocyclic means the cyclic structure purely made up of only carbon, right? So examples, if I take cyclopropane, cyclobutane, or you can take unsaturated compounds also here, cyclic compounds, cyclopentene and cyclohexane. These are whatever it may be, irrespective of whether saturated or unsaturated, the common thing is what they are made up of. The cyclic skeleton is made up of only carbons, so that we call it as carbocyclic compounds. Here heterocyclic compounds which have some hetero elements apart from the carbons in the cyclic skeleton, we may have oxygen or nitrogen, phosphorus, sulfur, right? So presence of hetero elements in the carbon cycle. So examples are this compound, we call it as piperidine or piperidine, and this is called morpholine, and this compound which I am going to write now, we call it as tetrahydrofuran, THF, a widely used solvent in the organic synthesis. This we will be using it frequently in the further chapters when we are doing some synthesis and when we are studying about the reactions. And these are a few compounds of heterocyclic. In aromatic, there are again 3 classes over there, right? Aromatic compounds are of 3 types. Okay, let's start the aromatic compounds. So aromatic I am doing here as we are not having the space over there. So aromatic compounds, generally students, for aromatic compounds whenever we talk, the first thing strikes in our mind, maybe from your lower classes also you might have seen, the first thing, the first molecule that strikes in our minds is benzene, right? So this is the representative of all the aromatic compounds. But there are some compounds aromatic without benzene ring also. So let me just take you through that. Aromatic compounds are benzenoid, which are having at least one benzene ring in them. Non-benzenoid, which do not have any benzene ring in them, but they are aromatic. And finally, heterocyclic aromatic compounds. Just now I told you what are heterocyclic compounds. Presence of hetero elements such as oxygen, nitrogen, sulfur, phosphorus in the cyclic skeleton. So benzenoid, best example is benzene itself, which have at least one benzene ring. Benzene. Naphthalene you might know, we use at home. We just keep those white color balls or different colors of balls in the almaris to prevent the insects to damage the clothes, from the damaging of clothes, right? And anthracene. These are all the products of the distillation of crude oil. And non-benzenoid means they are aromatic but they are not having any benzene ring. The best example for non-benzenoid category, and which we will be learning in the dipole moment topic also, this particular molecule. Remember this molecule, everyone. So this is azulene. And heterocyclic compounds, here also I will be giving you the examples, the frequently used or frequently pronounced compounds in our further chapters. The best example for heterocyclic aromatic compound is pyridine, widely used aromatic base in the organic synthesis. And this particular compound is called pyrrole. And this is called furan, right? Furan derivatives used in the making of perfumes, right? So that's how we can classify the hydrocarbons into their respective categories. So far you might have observed during this classification, right, carbons have connected in different ways. In different classes, carbon has the different connectivities. So based on the different connectivities, or based on the different mode of bonding, or based on the distance from a particular group, carbons can be classified into various categories, among which we will just go one by one. So classification of carbon and hydrogen. Carbon and hydrogen, among which the first classification that we are going to do is based on the connectivity. So based on connectivity, carbons are classified into 4 categories. Primary carbon, secondary carbon or 2-degree carbon, tertiary carbon or 3-degree carbon, quaternary carbon or 4-degree carbon, which means a primary carbon, the carbon which is directly attached with only one other carbon. So attached with one other carbon directly. Only one other carbon. A secondary carbon which attached with 2 other carbons directly. And the tertiary carbon which is attached 3 other carbons directly. And the quaternary carbon which attached with 4 other carbons directly. So that's how we classify the carbons into primary, secondary, tertiary and quaternary. Now everywhere, not only in this case, everywhere, whatever the nature of the carbon we denote, the same nature will be applicable for hydrogen also, which means what I am telling is, whatever the nature of the carbon, the same nature of the hydrogen also is applicable on which that particular hydrogen is present, which means whatever the carbon, for let me just take you through the hydrogens classification. So the nature of the hydrogen is equal to the nature of the carbon to which it is directly attached. So that's the meaning of the previous statement. So that is primary hydrogen. Primary hydrogen is what? Primary hydrogen directly connected with primary carbon. A secondary hydrogen which is present on the secondary carbon. A tertiary hydrogen which is present on the tertiary carbon. Just like quaternary carbon, quaternary hydrogen is not possible, because quaternary carbon means already it is having its valency field. So there is no chance for the quaternary hydrogen of existence, right? So just now I told the nature of the hydrogen is exactly equal to the nature of the carbon on which it is present or to which it is directly attached with. So based on this, let me just take you through some example. If I take this example, you might have seen that. What is the degree of this particular carbon? See, this carbon is directly attached with only this carbon on the right hand side. So can I say this is a primary carbon? Yes, we can. And with respect to this carbon also directly attached with only this carbon, no? That means this carbon attached with only one carbon connectivity. So we can say it as a primary carbon. And just now I told you the nature of the hydrogen is exactly same to the nature of the carbon on which it is present or to which it is directly attached with. And let's try a few more examples for this, and then we will go ahead with the next type of classification of carbon and hydrogen. I hope you understood this. This carbon is directly attached with only this particular carbon. So I can write it's a primary carbon, and the hydrogen, here it is primary hydrogen. And this particular carbon, if you observe the middle carbon, this carbon is attached with two carbons from both the sides. See, from this left hand side one carbon and from this side another carbon. So the middle carbon has directly connected with two other carbons. So according to the classification, we have to say it is a secondary carbon. And this is a primary carbon as well, you can see, right? So the hydrogens, what about the hydrogens? Since they are present on the secondary carbon, they are secondary hydrogens. And these three hydrogens present on the primary carbon, so we have to make them as primary hydrogen. And let me just take you through some more examples. If I take this particular example, right? So directly I am writing this is a primary carbon because it is directly attached with only one other carbon, and this particular carbon attached with, see, this one carbon, two carbon and three carbons. So this carbon attached with how many carbons? Three carbons directly. So we have to write what? Tertiary. This carbon, if you can see, two carbon connectivity, secondary. One carbon connectivity, primary. And this particular carbon attached with only one carbon, this carbon. So that's how we can classify the carbon. So for hydrogens, you don't have to do anything. Whatever the degree present on the carbon, the same nature hydrogen also gets if any hydrogen is present on that particular carbon, which is under our observation, right? So this one kind of classification. And let me take you through the last example. So let me also just illustrate with the quaternary carbon as well. So this is the quaternary carbon here, the one which I am marking with yellow, highlighting with yellow. If you can see this carbon has 4 carbon connectivities around it, right? So I can directly mark this particular carbon as a quaternary carbon, and this particular carbon, so whichever I am just circling with blue, I hope you understood this. All these carbons, if you clearly observe, they are directly connected with only one other carbon. See, this carbon has only connected with this carbon. So one carbon connectivity, and this carbon is connected with what? Only one carbon. So that's a primary carbon. This is also having only one carbon connectivity. This carbon is attached only with this carbon directly, and this particular last carbon, I mean the terminal carbon, directly attached with only one other carbon. So all these carbons I can mark primary carbons, and the hydrogens by default will be primary hydrogens, right? And how about this carbon? If you clearly observe, which I am highlighting this carbon has one carbon connectivity on this side and another carbon connectivity on this side. So we have to call it as secondary carbon, and the hydrogens attached with these are secondary hydrogens. So that's how we classify the carbons and hydrogens into their respective degrees based on their connectivities. Now, the second way of classifying them is based on distance. Based on distance means generally we take functional group as a reference. So from there we try to calculate the distance. Calculate means it's not a mathematical calculation, just a normal distance. How far, I mean, how many elements in between, how many carbons in between. It's just like a estimation, right? So distance from functional group. I'll tell you what is functional group when we were doing about the IUPAC nomenclature. We'll just, before the IUPAC nomenclature, we'll just go ahead with this. Okay, as of now, just remember. So from the functional group, let us say I'm going to take a carbon chain, and I'm just writing one hydrogen, because we are up to classifying the hydrogens and carbons only. So I'm only highlighting one carbon on each hydrogen and carbon. So let it be a functional group. Now, the carbon which is directly attached with the functional group, we name it as an alpha carbon. The hydrogen attached with the alpha carbon is alpha hydrogen. We told you, no, for everywhere it is applicable. Whatever the nature of the carbon is the nature of the hydrogen. So hydrogen's nature is always the carbon's nature. So whatever the denotation we use for the carbon, same is applicable for hydrogen on which it is present, right? So next to alpha is a beta carbon, and the hydrogen of the beta carbon, as discussed, that would be by default a beta hydrogen. And next to beta is a gamma carbon, and the hydrogen present on that particular carbon is a gamma hydrogen. Next to gamma is a delta carbon, and the hydrogen present on delta carbon is delta hydrogen. So that's how we can classify the carbons and hydrogens based on their distance from a particular functional group. And the last type of classification based on bonding. Based on bonding, but I hope you understood, already we have discussed saturated or unsaturated. So if carbon-carbon single bonds means saturated carbon, right? If carbon has a double bond, that's an unsaturated. And triple bond also we include with unsaturated categories. We have already discussed this, that's the reason I didn't go through it much. So that's how we classify the carbons and hydrogens based on the different references. Now let's have a look into, so far we have been doing about the introduction and the story behind the organic chemistry and classification of hydrocarbons and classification of carbons and hydrogens. Now we will learn how to represent an organic molecule. So I'd like to write here a representation of organic compounds. Okay. The first type of representation among is condensed formula. What is that? Condensed formula. In condensed formula, we only write the important skeletal bonds. We don't write all the individual bonds, right? Only the skeletal bonds or written. I'll write one more type of representation, and I'll take a single example and explain both the type of classifications with a single example. So the next classification, the next type of formula that we are going to see is complete formula. In complete formula, where we have to write all the individual bonds including the lone pair of electrons, we have to highlight here. So all the bonds and lone pairs to be written, right? So for this, for both of these classes, I am taking a single example. The example is acetic acid. See, acetic acid is also used in foods. We say vinegar, we use in food making. So vinegar nothing but diluted diluted acetic acid we call vinegar, right? So acetic acid, which has the formula of C2H4O2, right? So here if you write the acetic acid in this formula, or sometimes we can also write without showing that single bond also we can write. So this is what the condensed formula. So what is this? The condensed formula. If the same acetic acid, if I write in this way, the complete formula, that means this carbon-carbon bond I am writing first. So this is our skeletal bond, which is our reference to. And this particular carbon has 3 hydrogens. So I have to write all the bonds individually. And this carbon has a 2 oxygens connectivity, among which one is a doubly bonded oxygen, and this oxygen will have 2 lone pairs on it, and the other is a OH bond, and here also the oxygen will have 2 lone pairs as well. So this is a complete formula. And we can also say Lewis bond line formula, this particular representation. Next we would like to write about stick line formula. Stick line formula means it is the most convenient and easiest way of writing organic molecules. Even the bigger molecules also, by putting less efforts, you can easily write. See, for example, if you want to write a complete formula, you have to write everything. Even the condensed formula also requires some bonds to be written, but a stick line formula, as I said, which is the most easy and convenient way, but you have to be very cautious when I am explaining the rules how to write, right? We will do forward and reverse also we will write. How to write the stick line formula from a given condensed formula or a complete formula, or for a given complete formula, how to write the stick line formula. In both the ways we'll practice. So let's try to get the familiarity with this kind of representation of organic molecules. So the third type of representation is stick line, or we can also refer it as angle line or line angle formula. Angle line and line angle both are same, right? So angle line, I can write stick line or line angle, line angle formula. So in this, the first point, we always in every representation we are about to represent carbon bond first. Okay, it's all about how we are representing the carbon and the bonds present around it in a given molecule. Now carbon-carbon bond, right? This is a carbon-carbon bond. I refer this carbon-carbon bond as a line, right? Assuming that, what is this? It's a carbon-carbon bond, and both the ends of the line, what? The carbons. Ends of the line are assumed to be carbons. are carbon. So if I write this line means here is a carbon, here is a carbon. So you don't have to write the carbon. Simply you can write a line to represent a carbon-carbon bond. So in such case, you may ask that, sir, what about the hydrogens? You said that valency of the carbon is 4 and you wrote only one bond around the carbon. What about them? In such cases, whatever the bonds you can see around the carbon with your naked eye, apart from that, whatever the valence is left over on carbon, by default, you have to consider those leftover valencies are hydrogens. That means simply hydrogens implicit by default on carbon, right? If any atom present, if any atom other than carbon attached with the carbon, if that is not a CC bond, for example, CO bond present, CN bond can be present, CS bond can be present, CP bond can be present. What are these? NOP, nitrogen, oxygen and phosphorus. So if any hetero element present, or hetero element bonded with carbon, then that element should be written. You should not consider like this. You have to write that should be written. Let me just take you through an example. For example, I will take this methanol. Generally we call it as methanol or methyl alcohol. One carbon is there and I write. I assume that this is the carbon but oxygen is attached, no? So you have to write like this, which means this end is a carbon, so that this carbon has only one bond around it. Just now I told you the number of bonds present around the carbon which you can see, apart from those, whatever the valence is left over, by default you have to consider hydrogens. For example, let's take this. Around this carbon you can only see one bond. That means out of 4 valencies of carbon, you can see only one bond around it. That means how many valencies left over? 3 valencies are left over. By default you have to consider those, with respect to those 3 valencies, this carbon will be having 3 hydrogens. This is how it happened here. So you can see 3 hydrogens present here. So let me just take you through one more example regarding. I'll take a fundamental and a very small molecule here, a ethane molecule, which we can represent like this, which means the CC bond, this is a carbon and this end is another carbon. So around both, with respect to this carbon, you can only see one bond around it. So out of 4, only one valency you can see. The remaining 3 valencies are what? Hydrogens by default. This is the meaning of hydrogens implicit on the carbon by default. And this carbon, if you can see, this has only single bond around it. That means only one valency is filled. So remaining 3 valencies, you have to assume that 3 hydrogens. So that is what here happened. Both the carbon have only one bond, and that means 3 hydrogens they have. So that's how we can represent. So that's how we use the Sticklein formula to make an easy convention to represent an organic molecule. So in the previous examples, we have discussed only with the 1 carbon or 2 carbon examples. Let us see some bigger molecules which have more than 2 carbon-carbon bonds. So let me just take you through an example. I just take a propane, for example. Observe carefully, right? If I write this in a skeletal form, carbon, 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 without hydrogen. So without hydrogen means by default you have only one bond around this carbon. So by default you have to assume there are 3 hydrogens must be present on this carbon. They are there. This carbon around, you can see 2 covalent bonds around this carbon. By default you have to assume this carbon would be having 2 hydrogens on it. They are there. And just like that, this carbon also will be having 3 hydrogens, as it is having only one bond around it that you can see, right? Now 2 bonds, how we represent this, right? So the common point where the two lines are meeting, is a common carbon. That's a mutual carbon. So let me just write let it be A, B, C, carbon A, B, Z we will take. So let's not write C, again you have a C, so there will be a confusion. So I will write there is a bond between A and B. This is the bond present between A and B, and there is also a bond present between B and Z. That means this is the point where the two lines are meeting here. See, this is the point where these two lines are meeting. See, these two lines are meeting here, isn't it? So this common point, we consider it as what? A carbon. So that's how we use the stick line formula to represent an organic molecule. Now let's have a look into another example. CH3, CH2, CH2, CH3. So write the skeletal formula first. By leaving the hydrogens, there are three carbon-carbon bonds. That means three lines you will get in the formula. The first line, this is the line 1, 2, 3, 4. Carbon number 1, 2. And 2 also have the bond with the 3. So this is the 3. 3 also has the bond with the 4 apart from the 2. So that's how you can represent the hydrocarbon in a conventional way. So by default, if you see, let us take this carbon number 2. Around this carbon number 2, how many bonds you can see? There are only 2 bonds that you can see around this carbon. See, for example, if I start from here, only 2 bonds. See, this purple bond and the blue bond, right? So these are the 2 bonds. Since you can see only 2 bonds around it, the other default valencies are 2. That means there are 2 hydrogens. See, the carbon number 2 have 2 hydrogens. Around the 4th carbon or 1st carbon, how many bonds you can see? Only 1 bond you can see, so that they will be having 3 hydrogens by default. Got it? So that is how we represent and write the organic molecules in a easy conventional method. Let me take you through a bigger example now. CS3, try to learn it as quickly as possible, and this would reduce your efforts and a very easy way of representing. See, for example, let's write the skeleton. Directly I am writing 1, 2, 3, 4 carbons I wrote, and the second carbon has a methyl. So that's a very easy representation, right? Now we will do reverse. Reverse means, let me take you through some cyclic examples. For example, if I write like this, okay, don't mistaken that sir is writing triangle. It's not triangle. Yes, in the perspective of mathematics, it might be a triangle, but here it is a cyclopropane ring. See, at this point, this carbon I'm writing here, it has 2 bonds around it, and this carbon has 2 bonds around it, 1 bond which we have already written, and this carbon also has 2 bonds. Is that how a cyclic structure can be represented? So which means you can see only 2 bonds around this carbon, so this carbon would be having 2 hydrogens, and same for all the hydrogens with their respective carbons. So each carbon will be having 2 hydrogens. So all the cyclic compounds, I mean the unsubstituted cyclic alkanes, I mean all the unsubstituted cycloalkanes will have 2 hydrogens on every carbon, right? Except they are substituted. For example, here if you can see, it's a cyclohexane. So how can we represent CH2, CH2? I said only for unsubstituted. For substituted hydrocarbons, it depends on the number of substituents present. But without substitution, all the cyclic carbons have 2 hydrogens on them, right? For example, if I write a cyclopentane and like this. So how will we convert it? First I write the cyclopentane. Skeletal structure we have to write. So 1, 2, 3, 4, 5. right? Just for the sake of reference, I'm just labeling these carbons. 1, 2, 3, 4, 5. If you can see, the fifth carbon has one CC bond, which means one another external carbon, which is not the part of the ring. And this first carbon, see, 5, 4, 3, 2, 1. It has two bonds around it, right? So that's how we can represent, and by default hydrogens you can assume that, right? So that's how we use the Stickline formula to represent in a easiest way of organic molecule. So let us practice some more examples here. If you write like this, here itself I write the carbon, 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 right? So now we can write this as carbon, carbon, and one more carbon, and this carbon. Is it the same with the carbons? Now from the same example we will derive what we have classified before, primary, secondary, tertiary. If you can remember that, based on the connectivity we have classified the carbons based on the connectivity. If it is attached with one carbon primary, two carbon secondary, three other carbons tertiary, four other carbons quaternary. So let me just take the same molecule which I have written here. Carbon-carbon connectivity, here nothing but the number of bonds present around the carbon. So if you can see, this carbon has only one bond around it. I mean only one bonds you can see. Whatever the bonds you can see, those are the carbon-carbon bonds. Only carbon-carbon bonds we write in the Stickline formula. No, we don't write carbon-hydrogen bonds. So whatever the bonds you are seeing here, those are carbon-carbon bonds only. Now let us mark here, this particular carbon you can see only one bond. That means it has only attached with only one other carbon directly. So we have to write it as a primary carbon. If this carbon, if you see, this carbon has this bond and this bond, two carbons around it. That means two carbon-carbon bonds around it. So this is a secondary carbon. This is also same. This is also same. Now, when it comes to this particular carbon, if you see, first bond, second bond, and the third bond. So this carbon has three carbon bonds. I mean this carbon is attached directly with three other carbons. So we have to make it as a tertiary, and here it is secondary, here it is secondary, and here it is primary, right? So with the help of the Stickline formula, you can also write the double and triple bonds. For example, right, double and triple bonds. First we write, this is a primary carbon, secondary carbon, secondary carbon, secondary carbon, secondary carbon, primary carbon. Don't consider the number of bonds present between the carbon to classify the carbons into various degrees. You have to strictly consider to how many carbons it is directly connected, not between the number of bonds present, right? So irrespective of the number of bonds present between the carbons, you have to consider only the number of carbons that are directly connected. So here I can write CH3, if full formula, if you want to write CH3, this carbon has a double bond, this carbon has a triple bond, right? This is having a triple bond. So that's how we use the Stickline formula, and we represent with the Stickline formulas. Yes, so that's about the Stickline formula. Now let us move on to another type of formula. So better visualization, we'll try to represent the molecule in a three-dimensional way. That is, we'll start with the Fisher projection. The Fisher projection, right? So in this Fisher projection, what we do is, we try to represent the carbon-carbon bond with a wedge, or the bonds around the carbon with a wedge. For example, as we know that carbon can form four bonds around it like a tetrahedral, right? In this way, I write some wedges. which is a solid wedge, and I write a broken wedge. A solid wedge is assumed to be towards the observer, or when you're studying about a plane, we start it as a above the plane. And this is the broken wedge we represent. I mean, whatever the bond is represented with the broken wedge, we say this is away from the observer, or it is behind the plane or below the plane, right? Behind the plane or below the plane, molecular plane. Now let me just illustrate with the carbon bond. So in the Fisher projection, we write a cross, and the center of the cross we assume that's a carbon. So these are the 4 bonds that you can see around the carbon. So to represent in a better way, I write with a wedge representation. Got it? So it's a broken wedge which I'm writing now. You have that, right? Here it is a vertical line and there is a horizontal line. So the bonds present with the vertical line I just represented with a broken wedge, and the bonds present in a horizontal line with a solid wedge. Got it? So that's how a Fisher projection looks like. So which means the bonds present on vertical line, I mean the vertical orientation, whichever the bonds present are vertical, those are behind the plane or away from the observer, and the bond which are denoted horizontally, which are coming towards the observer. Let me just take you through a small example, a small convention with the help of these 2 chalks. So as I said, it looks like this, right? If you can visualize it. See this horizontal bond, that means the purple bonds which I wrote here, which are coming towards you. If I pass a plane through these 2 chalks, this is coming behind, right? As compared to this, is it away from you or not? Yes, it is. You are the observer. So from the observer point of view, this is going away from the observer or present behind the plane, and this is coming towards the observer and it is present above the plane. So that's how we represent a tetrahedral carbon in a possible conventional Fisher projection, right? To make it some more easier representation, we just go ahead with some upgraded one, that is 3-dimensional representation of a tetrahedral carbon. A tetrahedral carbon by using these wedges only. And to do so, I'll write one more small information here. The bonds which are indicated with a normal line, assume that those are in the plane, right? All the optical isomerism and stereochemistry is about these kind of representation. If you can visualize more in the 3-dimensional space, then you'll get more clarity on the concepts in the further chapters, right? After nomenclature, we will be dealing with the isomerism, right? 3-dimensional representation, right? In a 3-dimensional representation with the help of wedges or wedge representation, what I do is I write a carbon like this, a carbon, and I place the bonds around the carbon like this. 2 bonds are with the normal lines I am representing, and another 2 bonds with wedge representation I am writing, right? That's how. So now I can write this molecule as, without showing the carbon, you can write it in this way. this way, which means which bonds are going away from you? The broken wedge is going away from you as said, and the solid wedge which is coming towards you, and the normal lines, which are the bonds which are indicated or denoted with the normal lines, they lie in the plane. So for example, so let me just change the color of the bonds. Blue, the green, right? So here these are the bonds which are represented with green and blue, I mean with the normal line. So this is how a tetrahedral carbon looks like. So if you can see from your side, when we pass a plane through this molecule, if I pass a plane through this molecule, these two bonds comes in the plane, and the purple bond which is coming towards you, right, it is towards the observer, and the orange bond presented with the broken wedge is going away from you, right? This is behind the plane, this is above the plane or towards the observer, and these two are in the plane, the normal lines. So that's how we represent a tetrahedral molecule in a three-dimensional way, right? So this is the three-dimensional representation of a single carbon, right? Now let's have a look into how will you represent a three-dimensional carbon, I mean a CC bond in a three-dimensional way. So for that we need the help of Newman projection. What is that? Newman projection. Newman projection and Saar's representation, followed by this just the other way of representing a CC bond in a three-dimensional way, the extension of Newman projection, Saar's. After that we'll see it, right? So it is what? The representation of CC single bond. Now what I take is, I take a CC bond, right? CC single bond. Each carbon has identical groups, AA, for example AA, BB and CC. Now my reference is to represent this molecule in a three-dimensional way about this CC single bond, and I am telling you a sigma bond looks like this. Sigma bond looks like a cylindrical, see this chalk is the cylindrical shape, right, if I am not wrong, right? So yes, I am not wrong, it's cylindrical only, right? So you can rotate the groups. So around the cylindrically symmetric sigma bond, the rotation of the groups is very easy. That means free rotation of the groups possible around a sigma bond, I mean a CC single bond. So that is our key here, to rotate the groups. Later you may get a doubt, sir, how can we rotate the groups around the carbon as per our wish? Yes, we can rotate, right? So because of the sigma bonds symmetry. Now I just indicate with this carbon with a dot and this carbon with a circle, okay? It has nothing to do with the chemistry, just for the sake of representation I am just making them like that. Now I just write a carbon like this. What is this? The dot. The dot is what? Which is the front carbon, because if this is a carbon-carbon bond, if you assume this is a carbon-carbon bond, right, you are viewing, this is a carbon, this is a carbon, you are viewing the molecule in this way. That means, can you see this? No. So this carbon is exactly behind this, the front carbon. So the bond is coming into the plane. So you cannot see the carbon-carbon bond, right? Right. So the carbon-carbon bond goes into the board here. So this circle is the rear carbon or the back carbon, right? So this is a dot and this is a rear carbon. So as said, the bond present between this dot, I mean this carbon and the circle, the back carbon, is in the board. I mean it is in the plane just like this, right? Now let us mark the groups around them. This carbon has ABC around it, and the back carbon also have ABC around it. B, C, and this the front carbon also has. Now if you can see in such a way that if I assume that these two oranges are what? Orange arcs are A, and these are present around this bond. So this is the A of the front carbon and this is the B of the back carbon. Are they overlapping each other? Exactly. Can you see both the charts? No, you can see only one, the front one. That means the front and the back carbon bonds are exactly overlapping. That means eclipsing on each other. So this kind of representation in which the bonds are getting eclipsed over other, I mean the bonds of the adjacent carbons are eclipsing on each other, this kind of representation we call it as eclipsed representation, or in the terminology of stereochemistry we call it as eclipsed conformer. And by keeping one carbon constant, I can rotate the carbon, I mean the groups around the CC single bond. Just now I told you, due to the cylindrically symmetric sigma bond, we can rotate the group. So I just keep the sigma front carbon constant, I rotate the back carbon. Now you can see both the chalks, right? That means they are not eclipsed now. They are what? Staggered way. That means they are not overlapping on each other. They are in the staggered orientation, right? So that's how you are getting the different kinds of representations, isn't it? So if you view the molecule, it looks like this, sidewise view, right? So now by keeping the front carbon or back carbon, whatever it may be, but you have to keep one carbon constant and rotate the other carbon by 60 degrees or the multiples of 60 degrees. So I'm just rotating this carbon, I mean I'm just keeping the front carbon constant as said, and I'm rotating the back carbon. So if I rotate the back carbon, so let me just write the front carbon groups first, ABC, right? So constant. Now this A will be coming here due to the 60-degree rotation, this B will be coming here, and this C will be coming here, right? Due to the 60-degree rotation, A, B, C. So that's how we can rotate the groups to get the different types of orientations. And this is how we represent a CC single bond in a three-dimensional way. And the representation, the Newman's projection or the Newman's representation in which the bonds are eclipsing on each other, that kind of representation is called eclipsed Newman projection. And the one which are bonds are not overlapped on them, that is called staggered representation, eclipsed and staggered. So that's how we represent a CC bond in a three-dimensional way. And the last and the extension, see, so far in the Newman projection you have pursued the bond from a front side, head on head watching. Now if you view the same CC bond in a sidewise, that we call it as a Sahar's representation. So Sahar's representation is a sidewise. What is this? Head on head and sidewise. Sidewise view of Newman projection is nothing but what? Sahar's representation, in which front carbon I am writing, just drag it out of the plane, drag it out of the plane sidewise, drag it out of the plane sidewise. So let me just illustrate that. This is the CC single bond as discussed, and this is the front carbon where ABC are attached. This is the back carbon where ABC are attached. See, A and A are overlapping. If you view the molecule from in between these two bonds, both the C's are coming towards your left hand side and both the B bonds are coming towards our right hand side, and both the A's are like flagpoles overlapping each other. So which we call it as eclipsed Sahar's representation. And by rotating it, this carbon 60 degrees, we will get the staggered representation, right? I'm just writing here. So again I'm just keeping the front carbon constant, so ABC constant on the front carbon, whereas on the back carbon I'm rotating the groups where A comes here, B goes here and C comes here. So this is called staggered. So that's how we represent the organic molecules, by using different kind of representations and the tools. So that's about the representation of organic molecules. Now let us build some fundamental tools which are required to study the further level of organic chemistry. First of all, we build the fundamental tools which are required to name the organic compounds. So let us start with, as we discussed, the hydrocarbons are the fundamental organic compounds. So we discuss about the types of hydrocarbon groups. Types of hydrocarbon groups. What is this hydrocarbon group? It is as simple as that. When we are doing the nomenclature, the hydrocarbon groups present as substituents. In such case, what do we have to name it and how do we have to name it? For that thing, we are just doing a small exercise here. That's all, right? So a hydrocarbon group, which means removal of a hydrogen. For example, a hydrocarbon, I write with a RH. I am not writing whether it is saturated or unsaturated. It doesn't matter. Holistically, I am just taking, without mentioning saturated or unsaturated, I am just taking a hydrocarbon. By removal of a hydrogen gives hydrocarbon group. Removal of a hydrogen from a hydrocarbon group gives you the hydrocarbon group. So this is the respective hydrocarbon group. Now we will go individually, right? Alkane, alkene, alkyne, which means what type of hydrocarbon groups can be given by an alkane family and by an alkene family, by an alkyne family, right? So let us start with an alkane. Right? An alkane, on removal of a hydrogen, gives alkyl group. So if you can clearly observe, the word AN, AEN has been replaced by YL after removal of a hydrogen. See? Right? For example, alkanes have two types or three types, branched and that. So first, fundamentally we know from the knowledge of our lower classes, N alkanes and branched alkanes. So alkanes are of different types. What are those? Straight chain, which are called N alkanes. Right? An alkane. N means normal. A straight chain alkane, generally we say it as a normal alkane. Right? So let it be 1 here. So an alkane gives N alkyl group. As we say, no, just now, from any alkane, if you remove the hydrogen, that gives you alkyl group. If it is an N alkane, just replace. It doesn't matter N or something else we are taking. It only matters that you have to remove this AN with IL. Replace this ANE with a IL. So you will be getting alkyl group. Which alkyl group we are going to get? N alkane is giving N alkyl group. Right? One more time, I am just highlighting it. Right? N and IL. So if an example, CH3, CH2, CH2, CH3. Remember this example. Again, we will discuss in another context, the same example. Definitely you will get a doubt about this molecule. So that's why I am telling here itself. So N-butane, right? So an N-alkane gives the N-alkyl group when the hydrogen is removed, I mean the removal of hydrogen from any one of the terminal carbons. Right? What are the terminal carbons? Last carbons of the chain. Right? So that means to obtain an N-alkyl group, for this example an N-butane, either you have to remove the hydrogen from this terminal, I mean the last carbon, or you have to remove the hydrogen from this particular carbon. Only from the terminals you have to remove, any one of the terminals. It's up to you. You may remove from here or you may remove from here. So since I'm a right-hander, so I will be removing from far right hand. If you are a left-hander or you would like to have this kind of orientation, you may also replace the hydrogen from a left-handed terminal. Right? So CH3, CH2, CH2, CH2. So this is where I just replaced a hydrogen. So what should I write? Butane will be giving you what? Butyl. So N is common. So that's how we get it. And you may think that, sir, what happens if we remove a hydrogen apart from the terminal carbons? There are some internal carbons present. What will it give? We will see in a short time. Right? After giving some fundamental basic examples, we will definitely come back to it. That's why I told you to remember this example. Right? So this is how an N-alkyl, and let me just take you through some more examples of the same category. So directly I am writing N-pentane, which has 5 carbons. Right? What is this? N-pentane. So I'm just removing the hydrogen from this particular terminal. So will be obtained an N-alkyl group, which means since alkane is pentane, so we'll be getting an N-pentyl group. Right? If it is a cycloalkane, let me just highlight one carbon hydrogen bond. Cycloalkane means whatever it may be, as I said, N-butane or cyclobutane, it doesn't matter. Replace the AEN ane with YL-yl. That's all. So what is this? Cyclohexane. If you remove this hydrogen, only hydrogen. See, if you can observe here, we are retaining the bond here. The fourth bar, and we are not removing the bond, only hydrogen alone we are removing. Remember that this will be discussed again in the context of inductive effect. Right? So this we call it as cyclohexyl. So which means what? A cycloalkane on removal of hydrogen gives cycloalkyl. Same as open chain alkanes, just we mention one extra word, that is what? Cyclo here. Right? Right. So that's all about the open chain alkane, that means a straight chain alkane and its respective alkyl group. Now the branched chain alkanes and their respective alkyl groups. Let's have a look into branched. In the branched chain alkanes, first I'll tell you what are the branched type alkanes and what are those types. In this category we have isoalkanes and a neoalkane. Right? An isoalkane is the one, the presence of one methyl group on the second last carbon of the chain, or last but one carbon of the chain, second last carbon of the chain. Right? So for example, this is the carbon, the last carbon I am taking. For example, if I take this, I assume that this is the last carbon from this side and this is the second last carbon. So if any group present here, I mean if any carbon present here, we call any alkane which have this kind of structural unit as isoalkane. So now I am just removing it. So now what is this? This is the structural unit of what? Iso. Any alkane which have this kind of structural unit in it from any one of the terminal, we have to tell it as isoalkane, right? Then let me just construct some examples. For example, if I write CS3, CS3 and CS3, right? This I see from this terminal, or both the terminals are equivalent. If you clearly observe, from any one of the terminals you can consider. So I consider because from this it is more convenient to represent, right? So this is the last carbon and this is the second last carbon which has a methyl group. So do we have the structural unit of iso here? Right? This is iso. Structural unit is present. Iso. What are the total number of carbons now? 1, 2, 3, 4. The structural unit itself has 3 carbons. So total number of carbons 1, 2, 3, 4. 4 carbons means you have to write butane. So what is the name here? Isobutane. That's all. And one more example for this. CH3, CH3, CH2, CH3. And you have iso again here, if you clearly observe. So I can write iso. What are the total number of carbons present in the given hydrocarbon? 1, 2, 3 in the structural units itself. Apart from this, 2 more carbons. 3, 4, 5. So 3 plus 2, 5. So that means isopentane, right? Now, how will we write a neoalkane? What is a neoalkane? First we will learn what is isoalkane and what is neoalkane. Then we'll look after what is isoalkyl group and what is neoalkyl group. So a neoalkane, presence of 2 methyl groups on the second last carbon of the chains. The only difference is one more extra methyl group present on the second last carbon, so that we can call it as such type of alkanes which have such kind of structural unit or the arrangements in them. Those are called neoalkanes. So let me just take you through some examples. So I'm just writing the neo here so that I'm just leaving some space. Later we will write the respective alkyl groups here itself, right? So here, so for neo, just drawing a line here, CH3, CH3, CH3. So this is the structural unit of what? Neo. This is the last carbon and this is the second last carbon which has 2 methyl groups. So the structural unit of neo. So if you would like to give some examples for the same, let me just take you through this one. See, the structural unit itself is consuming 4 carbons it requires, which means the smallest neoalkane, at least if you have 1 carbon, you can say it as a neoalkane. The smallest neoalkane is what? Neopentane. So let me start with that only. So since both the ends are equivalent, so from any one end you can conclude it. So this is the structural unit of what? Neo. The total number of carbons are what? 5 in the given compound. So I have to write neopentane. And the same for, if I would like to write neohexane, first for neohexane means hexane. The name itself is telling it will be having 6 carbons in it. So neo says you have to write a neo structural unit. So after writing the neo structural unit, which have 2 methyl groups on the second last carbon, out of 6 carbons, we only left with 2 other carbons. So write the 2 carbons in a straight chain way. So this is called neohexane, right? So this is how we can write neohexane, neopentane under the category of neoalkanes, and isopentane, isobutane under the category of isoalkanes. Now, how will we get the respective neo-alkyl group and neo-alkane group, right? From iso and neo, they will give the respective alkyl groups when we remove. So, removal of hydrogen from the opposite terminal of structural unit. What is the structural unit? Let me just illustrate with this. So you can't remove the hydrogen from wherever you want. You have to remove the hydrogen only from the opposite terminal of the structural unit, so that they will give their respective alkyl groups. For example, in this isobutane case, this is the structural unit, I mean this is the terminal of the structural unit, and the opposite terminal is this only. So if you remove the hydrogen from this terminal, you get isobutyl group. So opposite terminal of the structural unit. So this is the opposite terminal of the structural unit, and I have removed a hydrogen. So this is what? Isobutyl group. If I would like to make an isopentyl group, where do I have to remove the hydrogen from? If this is the structural unit, then this is the opposite terminal of the structural unit. So you have to remove the hydrogen from here, so that I can write it as isopentyl. And the same is applicable to create or to generate a neo-alkyl group from their respective neo-alkanes by removing a hydrogen from the opposite terminal of the structural unit. In the case of neopentane, this is the structural unit on the left hand side, and this is the right hand side terminal, opposite terminal. So from here you have to remove the hydrogen to get a neopentyl group. Yes, I just removed a hydrogen, so which we call it as neopentyl. And if this is the structural unit of isohexane and this is the opposite terminal, so that we will get a neohexyl group by removing a hydrogen from the opposite terminal. So I can write it as neohexyl, right? So that's how a neo-alkane, neo-isoalkane and their respective alkyl groups are obtained. So as I was discussing, what happens if the hydrogen is being removed apart from the mentioned carbon? Mentioned carbon means the particular classical carbon to get a particular alkyl group, like an alkyl group, isoalkyl group, neo-alkyl group, right? So an alkyl group will be getting obtained only by removal of hydrogen from the terminal, and an isoalkyl group is obtained when we remove only the hydrogen from the opposite terminal of the structural unit. Same as for the neo. What happens if we remove the hydrogen from the other carbons rather than the particular terminal carbons? So let me just explain that. I told you to remember this example. Right? So secondary, right? So I'd like to give you a point here. If the hydrogen is removed from a non-classical carbon of a hydrocarbon the alkyl group is named after the degree of the carbon from which the hydrogen is being removed, right? Non-classical carbon means, what is classical carbon? Particularly we have mentioned only from the terminals of the structural unit. Apart from those carbon, we say it as a non-classical carbon. So here, if you remove the hydrogen from such kind of carbons, you have to go according to the degree of the carbon from which you have removed the hydrogen. So let's take this example now. Now I am writing the same molecule again here. So if you remove the hydrogen from a classical carbon, which means the terminals, that will give you the respective N-alkyl group. But these two carbons are identical if you clearly observe. So let us remove the hydrogen from this. So what do you get here? It's a non-classical carbon, so that you get the hydrocarbon group based on the degree of this particular carbon. So as I mentioned, this carbon is a 2-degree carbon. That means a secondary carbon which has been attached with 2 other carbons. So it's a secondary carbon. So you have to write secondary. So to abbreviate it, sec you can write. As usual, you have removed the hydrogen from a butane, so you have to write butyl, secondary butyl. If you remove the hydrogen from a terminal, means N-butyl we used to write, right? Now we have removed the hydrogen from a secondary carbon of the butane, so we have to write it as secondary butyl. And for the same, if I take an isobutane we have practiced in the case of isoalkyl group, right? There we have removed the hydrogen from here. But what happens? This hydrogen is being removed. So now if you remove the hydrogen from this particular carbon, what is the degree of this particular carbon? It's a tertiary carbon, right? Let me write it a little bigger. So it's a tertiary carbon. So if you remove, that is also a non-classical carbon because we are not removing the hydrogen from the terminal carbon with respect to the structural unit. So this called tertiary butyl, or in the name if you want to write tert butyl, tertiary abbreviation tert we write, so tert butyl group. So that's how we name the hydrocarbon groups when the hydrogen is not removed from a classical carbon, right? So this is about the different types of chain orientations of alkanes, I mean the N-alkanes, isoalkanes and neoalkanes and their respective alkyl groups. Now let us start with alkenes. Okay, alkenes and their respective groups. See, we don't discuss much about the alkenes hydrocarbon groups as we discussed about the alkenes. We only discuss about the frequently used hydrocarbon groups which are derived from the alkene family. That's all. Okay, that is enough for our study. For example, alkene, when a hydrogen is removed, you have to remove this E, the last E with "-il", alkene plus "-il". So which is being removed? I mean this E is replaced with "-il". So which means what? Alkene is giving alkenyl group. So the starting member of the alkene family is this one, which is ethene, right? So if you remove a hydrogen from, because both the carbons are identical here, so you can remove hydrogen from any of the carbon. So I have removed from here. So what is this? Ethene. So this E should be replaced by "-il", ethenyl, right? This ethenyl group has a common name and widely we pronounce it in the further organic chemistry and in the reactions, which is called a vinyl group, right? Vinyl group. And double bond we consider as a functional group, right? So as we said in the classification of carbons based on the distance from a functional group, right? If you consider this as a functional group, Is this the carbon directly attached with the functional group? Yes, the double bonded carbon is a functional group, so that this is the carbon which is directly connected with the functional group. So we have to name this carbon as alpha carbon, right? So with respect to a double bonded carbon, alpha carbon is called allyl carbon. So let's not write here so that you will get confused, that name is given to the entire compound. So only this particular carbon is allylic carbon or allylic carbon or allyl carbon, right? If you remove a hydrogen from this particular carbon, the hydrocarbon group, I mean the alkene group which you are gonna get is an allyl group. If you remove the hydrogen from this particular carbon, you will be getting a CH3, and this is propenyl. Is it looking like a iso group, presence of a methyl group on the second last carbon? So we can write isopropenyl group. And if the hydrogen is removed from this particular carbon, you have to write it as propenyl group. Right? So propenyl, allyl and isopropyl. So these are the frequently used hydrocarbon groups from the family of alkenes. Next, from alkynes. Alkynes also same as alkenes. The E will be replaced by IL. I mean IL means IL. YL you have to replace. So alkyne, when you remove the hydrogen, you will give alkyne plus IL, right? So here the starting member of the alkyne family is this, which is ethine. If you remove the hydrogen from it, it will be giving you ethene plus IL, ethinyl. See, the E is replaced with IL, right? And if you take the molecule of propyne, this is propyne, right? If the hydrogen is removed from this end, we write the hydrocarbon group as, yes, we have to remove the hydrogen from here. So this is called propionyl, right? Or else if the hydrogen is removed from here, we have to write it as this is propargyl group. This is called propargyl group. So these are the types of hydrocarbon groups from their respective hydrocarbons. I mean from the alkanes, alkenes and alkanes, and these are the frequently used hydrocarbon groups. So now let us start with the new topic, that is homologous series. A homologous series is a group of compounds which have a similar chemical properties, and any two successive members of the group will differ with a CH2 unit. So what is homologous series? A group of compounds having similar chemical properties. I'm just putting in the words whatever I said. So similar chemical properties, among which any two successive members differ in a CH2 unit, right? Let me just tell you in terms of mass. A CH2 unit, meaning carbon, we know that atomic weight of carbon is 12 grams, right? Each hydrogen 1 gram. So both the hydrogens togetherly 2 grams. That means in terms of mass, if you want to express, any two successive members of a homologous series differ with 14 grams of mass or 14 units of mass, right? So, and I just mentioned here, let me just highlight this. Similar chemical properties, if you can observe that statement, similar chemical properties, which means they will be having the same functional group, right? So, functional group, let me just tell you what is a functional group now. Again, we'll get back to this homologous series. Functional group, a chemically reactive part. Chemically reactive part of an organic molecule. Chemically reactive part means it is the responsible for the chemical properties or the chemical behavior of the molecule, no? So that means, so the functional group is responsible for the chemical behavior, which means similar chemical behavior means, now you can connect this. Functional group means responsible for the chemical behavior. Similar chemical behavior means similar functional group as well. So I can conclude that, therefore, the compounds of a homologous series will have a same functional group, then only they can show the similar chemical properties, right? So, without writing directly that conclusion, better we just discuss with an example. Now, this is the example I am taking. Methanol, methanol we can also call methyl alcohol. This is ethanol, we can also call ethyl alcohol. If you clearly observe, CH3 common, OH common. In the alcohol family, this is the first member and this is the second member. So any two consecutive members are differing with what? A CH2 units. Is it clear now? But how can we say they are chemically similar, and how can you say they have similar chemical properties? Let's just check with a reagent. Generally alcohols are acidic in nature, so that definitely respond towards a metal. So I add a metal, sodium. Metal replaces the hydrogen, acidic hydrogen of acid. So here the hydrogen which is attached with oxygen is the acidic hydrogen. Let us check whether both are behaving similar or not. Yes, hydrogen is being replaced by sodium here, and here also hydrogen is being replaced, right? So in both the cases I write H2 gas, right? Don't bother about the reaction balancing, okay? Just clearly observe that what we are up to about these two reactions. That means which is responding towards a reagent, sodium, OH group. In both the cases, OH group is responsible for this reaction from both the compounds, isn't it? So can I say the chemically reactive part of these alcohols is OH? So we can conclude OH is the functional group of alcohols. So whatever the compounds which have OH functional group, all will undercome as the family of alcohols. So now when we arrange them in a proper sequence, you get a homologous series where the any two consecutive members will differ with a CH2 unit. I hope it's understood now what is homologous series and functional group, right? So functional group is responsible for the chemical behavior of the substance. But how about the rest of the part? You may think that, sir, OH is influence the properties. I mean, the functional group is responsible for the chemical behavior. But what about the rest of the part? For example, let us take the methanol part. Methanol's mass is 12 grams for carbon, 16 grams for oxygen, 28 grams and 4 hydrogens. That means 4 grams. So 32 grams, right? And the next member in the family, you have to assume that. So you don't have to calculate separately. You know that any two consecutive members or successive members of a homologous series differ only with the 14 units of mass. Add 14 to this, right? So what is this? 46 grams. And you know that physical properties are influenced by the rest of the part of the molecule, which means boiling point, density, melting point, all are directly proportional to molecular weight. That means, let me just take this as compound number 1 and this as compound number 2. So all these properties, compound number 1 less than compound number 2. More is the molecular mass, more is the density, more is the boiling point, more is the melting point, right? So that's how a functional group influences the chemical properties, whereas the rest of the molecule influence the physical properties, right? So final conclusion I'm just writing here. So functional group influence what? Functional group influence chemical properties and remaining part of the molecule influence physical properties. Right? Now let me just give you a few more examples regarding the homologous series. The family of alkanes, and moreover, since they have the same functional group and same molecular structure, they will be having same molecular formula as well. That means compounds of a homologous series will have the same molecular formula also. So I can write here compounds of a homologous series have same functional group and same molecular formula. Fg means functional group, MF means molecular formula. Now let me just give you some examples, right? So here I would like to take the family of alkanes first. Alkanes molecular formula is CN H2N plus 2. So the starting member is what? CH3H. Methane I just write like CH3H to highlight it. So this is CH3CH2H. CH3CH we can write in this way. And propane, if you can check, all are having the same molecular formula. Now let me take carboxylic acids. Whose molecular formula is CN H2N O2. So here first I write the formic acid, next I write CH3COOH. CH3COOH you can write to just highlight the CH2 unit, you can write in this way, and you can also write, and alcohols anyhow we have represented here. So alcohols have the molecular formula of, both are these what? Alcohols have the molecular formula of CN H2N plus 2O. Okay, this is the general molecular formula of alcohols, alkanes and carboxylic acids, and a few examples of homologous series. Yes, so that's all about the homologous series and this. And in this session, if you remember students, let's have a quick prerequisition or a quick revision about the session what we have discussed. So we have introduced the organic chemistry and the origin of organic chemistry, naming, and what are the fundamental organic compounds, and we have derived that hydrocarbons are the fundamental organic compounds, and later we have gone through the classification of hydrocarbons, and after that we have discussed about the types of carbons and hydrogens based on the connectivity, based on the distance, based on the mode of bonding, and later we have discussed about the representation of organic molecule. So the way of writing organic molecules, in that we have gone through various representations like complete formula, condensed formula, stick line formula. These are the normal representations, and later we have learned some other representations, a conventional three-dimensional representation of organic molecules like Fisher projection, wedge representation, and the CC bond representation by using Newman projection and Sahar's projection or Sahar's representation. So these are the representations of organic molecules, and later we have started off the discussion of the types of hydrocarbon groups, in that open chain hydrocarbon groups and N straight chain hydrocarbon groups, and what are branched chain hydrocarbon groups, their common names and their respective alkyl groups. I mean isoalkyl group, deoalkyl group, how we have obtained them from their respective isoalkane and neoalkane, and later we have discussed about after that the type of hydrocarbon groups that have been obtained from an alkene family and alkane family, and finally we have started discussing with the homologous series and the functional group and the types of homologous series and their respective properties of a homologous series. So this is what we have discussed in this session, and in the next session we will be learning, the second session we will be learning the further more topics of organic compounds, right? So that's all about the session. Thank you so much.